Hi, good day, and welcome to the Division of Education, Innovation and Energy e-learning program. I'm one of your facilitators, Joseph Frederick, in the area of mathematics. And for this video, we shall continue our exploration of algebra by focusing on binary operations. Our objectives for this video are to explain the term binary operation. At the end of this video, you should be able to explain what binary operations are. You should then also be able to use binary operations to solve problems in mathematics and in algebra. Questions focusing on binary operation are usually found in question number 2 of a paper 2 section 1. Also, we want to do an exploration. We want you at the end of this video to describe the distributive property and solve problems utilizing the distributive property of multiplication over addition and subtraction. So at the end of this video, our hope is that you will be a master in binary operations and distributive property by achieving these objectives. So, binary operations, that's where we want to start. So the first question that we have, that you should have for anything that you are going to encounter for the first time. The first question that you need to answer is, what is this thing? What is the definition that will satisfy whatever this new concept that you are attempting to learn? What definition would satisfy that? Our new concept for this video is binary operations. So our initial question is, what is binary operations? Can we describe binary operations? We are saying a binary operation is any operation that combines two elements to produce a third element. For example, I know all of you like punch, and I view the punch making process as a binary operations process, where I would take banana and the other ingredients, combine them together in my blender, and out comes banana punch. I would take peanut and the other ingredients and combine them together, and I get my peanut punch. Here in mathematics, we are focused in algebra, so we shall be using some variables. I take variable x, I put it into my blender. I take variable y, I put it into my blender. My blender, using its binary operation skills, produce a combination of x and y. This here is my third element. So what we have done is that we have taken x and we have put x as one element. We have taken y, we have put y as one element into our blender that combines it to create a third entity called x and to a triangle y. Now, triangle is a symbol that we use sometimes to represent binary operations. There are other symbols that we use to represent binary operations, and some of these symbols are, so when working questions involving binary operations, you may most likely see any one of these symbols. Now, the operations represented by these symbols can differ. So, by that we are saying here that, look, that here we have the binary operation triangle. This binary operation can be represented by any one of these symbols. Symbol here, any one of these symbols represent the same operation. We have taken m and n and we have combined it via this binary operation, combining it to produce m squared minus mn. Now this symbol, we can use any one of these symbols. As in algebra, we can utilize any symbol to represent a particular number. So here in binary operations as well, we can utilize any one of these symbols to represent a singular binary operation. What these symbols represent can differ. Once the definition of the binary operation is known, we can apply its use to similar situations. Here's an example. Given that m, this here represents our binary operation, and the definition of it is that here the m is first in front of the binary operation, the n comes after the binary operation. So based on the definition here, it's whatever is in front of the binary operation is squared, as we see the m is squared, and what comes after, what do we do with what comes after? What comes after, we multiply it by what comes before the binary operation and then subtract it from the square of what comes first. So now they define the binary operation for us, and then they ask us to evaluate 5, the binary operation 2. based on the definition of it, what comes first has to be squared, and then we subtract from that the product of what is in front of the binary operation and what is behind it. So therefore, that is going to give us here, that is going to give us here, so therefore, we have that it is 5 in front of the binary operation, 5 squared, minus the product of what is in front of the binary operation by what is behind that binary operation. And we get that to give us, what is 5 squared? 5 squared is 25, and 5 times 2. Remember, when working any problems in mathematics, we must use BODMAS. We must use our law of integers. So based on BODMAS, we were supposed to do the orders first. 5 squared is 25, and then we have a product occurring here. We do that product, it's going to be 5 times 2 is 10, so it's 25 minus 10 gives me 15. Let's look at another example. Given that, here is my operation, given that x, this binary operation here now, what does that represent? X, this here is our definition line. It defines the binary operation. It says that x, here it's box with a curve, here x box with a curve. What do we do once we see in this situation based on this definition? Remember, if I see this here for another binary operation, it may mean something totally different. But for this one here, what does it mean? X, box with a little curve on the right hand side, y. This is take the y divided by the x, or we should say, take the second element, take the element that comes after the binary operation and divide it by the one that is in front of the binary operation. Then, from that, we subtract 3 times whatever is in front of the binary operation. So, again, you just recall what this binary operation here indicates. It indicates that whatever is in front of the binary operation has to go and divide whatever comes after the binary operation. And then we subtract from it 3 times whatever is in front of the binary operation. So if you look here, we have numbers now, 2 binary operation 8. What do? Take whatever is behind the binary operation and divide it by what is in front of the binary operation. From that, we subtract 3 times whatever is in front of the binary operation. Once we have that line, the next thing to do is utilize our laws of integers and BODMAS. So we are going to divide first. So what we get here is 8 divided by 2 is 4, and we are subtracting from that 3 times 2. 3 times 2 is 6. So it gives us here -2. Again, remember, we did in the previous videos the laws of integers. 4 minus 6, the signs are different. Subtract the smaller from the bigger. Once we are adding and or subtracting our integers and the signs are different, we subtract the smaller from the bigger and carry the sign of the bigger. This is really nice. Look here at this one though. What if they now want us to find, look here, this is nice. What if they now want us to find, here in brackets, 2, the same binary operation, these 2 questions are related. So this binary operation would mean the same in this instance as well. So what if they wanted us to find now 2, the same binary operation 8, close brackets, then that same binary operation 10. How do we work that? We work out what's in the brackets first. But hey, we did that already. We worked out that 2 binary operation 8, we worked that out already. What did that give us? That gave us -2. Yes? So it's now going to be -2 binary operation 10. Based on the definition of the binary operation, that is going to be take whatever comes after the binary operation and divide it by whatever is in front. And then from that we subtract 3 times whatever is in front of the binary operation. So this here gives us 10 divided by -2. -2 is in front of the binary operator, so it becomes 10 divided by -2, subtract 3 by what is in front of the binary operation based on the definition. What is in front of the binary operation is -2. Now our laws of integers come into play. So we are going to do our division. 10 divided by negative 2, based on my laws of integers, is going to give me, correct is right, it's going to give me negative 5. However, negative 3 by negative 2, signs are the same and I'm multiplying, answer is going to be positive. So now I have negative 5 plus 6. Negative 5 plus 6 is going to give me, correct is right. Once signs are different, we subtract the smaller from the bigger and carry the sign of the bigger number. So that's how we do our binary operations. Ensure that you utilize whatever the definition is for that binary operator. Whatever that definition is. Here's another one. Look here. So, given that another binary operator, B is equal to B minus A all squared. Can we evaluate 7, that same binary operator, 3. And also, here's what they want us to find. Prove that the binary operator is commutative. So, let's do the first part. Doing the first part here, what is the definition that we are to use for this binary operator? The definition that we are to use for this binary operator is that this, it looks like a star to me, this star operator here in this instance, this star operator here, what does it mean? It means you take the second or what comes after the binary operator, and from that you subtract what is in front of the binary operator. And the answer that you get, you square that answer. So 7 star 3, again, please recall what the binary operator is. The binary operator is, again, this star operator. Whatever is behind the operator, we take that and subtract from it what is in front of the operator and square that. So we end up with here that 7 star 3. What is behind the operator? Behind the operator is 3. We are going to take that and we are going to subtract from it what is in front of the operator and square that. So we are acting here. Here we are acting as if B is 3 and A is 7. So we are going to come back to a definition line and replace B with 3 and A with 7. That's another way that you can look at it. So replacing B with 3 and A with 7, we end up with this. And now we utilize our laws of integers. Utilizing our laws of integers, we get that 3 minus 7, remember what it says, board math says, work out in the brackets first. So 3 minus 7 is negative 4. And then we have to do negative 4 squared. Negative 4 squared is 16. So that's our first part. We evaluated 7 star 3. The second part of it is to prove that the star operator is commutative. We looked at commutative in a previous video. We said that the commutative property is a property that says that regardless of how the numbers are ordered, there are two operations that we looked at that were commutative. Regardless of how the numbers are ordered, for addition and multiplication, the answer is still the same. So we said that addition and multiplication were commutative. By that we mean that 3 times 7 is going to be the same as 7 times 3. The order is the same. Or 3 plus 7 is the same as 7 plus 3. So we are saying that here is what addition and multiplication are commutative. Now what they want us to prove is that this star operation is commutative. So therefore, we need to prove that, so to prove that the star operation is commutative, we must prove that 3 star 7 is the same as 7 star 3. So we need to find 3 star 7. What is 3 star 7? 3 star 7, remember our definition of our binary operator. The definition of our binary operator in this instance here, that star operation, is that A star B is equal to B minus A all squared. So here, 3 star 7, whatever is in front of the operator based on this, or we can say, here's what. In this case, A is 3 and B is 7. So we're going to come across to the right hand side and replace A by 3 and B by 7. So it becomes 7 minus 3 all squared. Once we have this line, our next step is simply to use our laws of integers. What are our laws of integers? 7 minus 3 squared. 7 minus 3 squared is going to give us 4 squared. What is 4 squared? 4 squared is 16. So here we have 7 star 3 giving us 16. And here we have 3 star 7 also giving us 16. The order seems not to matter. The answer is still the same. Therefore, since 3 star 7 is equal to 7 star 3, then we can say that the star operator in this instance, is commutative. So that's it for binary operations.